Hey NXP, you've got a demo board offer for the I2C bus. I've got an idea, I need your board, so here's the deal. I want to build an LED grow light, but not just a red and blue LED thing. I want to do a microprocessor controlled LED grow light so I can really optimize the energy usage, but also because it'll run on the I2C bus, I want to be able to throw things like real-time clocks, A to D converters, general purpose I/O expanders, and everything under the sun on there, and make it this massive, uberly cool greenhouse controller. But we're going to start out just with an LED grow light controller. Got to start first and, walk before you run, so to speak. So let's take a look at the photochemical efficiency versus wavelength curve for plants, and then that'll be our basis for further discussion. If you take a look at this photochemical efficiency versus wavelength curve, you'll see I've superimposed the spectral output of typical LEDs. You'll notice that the greatest photochemical efficiency occurs at deep blue and dark red areas of the spectrum. Now, as one might expect, such as this is the area where most LED grow lights are advertised to operate. And I hope they do, but as you can see, the peak spectral output of LEDs and the peak spectral efficiency of plants aren't exactly lined up. So the manufacturers have to do some game playing or else really creative marketing. I don't know which they do, but that's something we want to look at. Another thing to note on this graph is you'll see that photochemical efficiency doesn't drop down to 0 outside in the red and blue areas. Yeah, it drops off quite a bit, but it's still there. And I wonder if that plays into some nutritional aspects. I know specifically the beta carotene functions deal with some of the amber and maybe even some of the green light energy for their part of the photochemical efficiency curve. I don't know, but it's something I want to take a look at and research. I want to go off topic just a little bit and discuss greenhouse heating. One of the big differences between the indoor, miniature little greenhouse and the commercial greenhouse is the way they're heated. A typical heating device for the small indoor greenhouse is the home furnace, and then an auxiliary heating pad, which is typically a flexible heater with nichrome wire in it. Pretty simple device, 100% electrical energy, and you get 100% heat out, and that's all you get. Now, in a commercial greenhouse, you're typically using a natural gas heater or a propane heater, and they're not 100% vented, except maybe in California and some other states where they've got an issue with venting stuff. But what happens is the combustion byproducts are turned into CO2, and the plants use that, and you get better growth rates. In fact, some places actually go so far as they have little CO2 burners in the greenhouse, so that when the CO2 levels drop down, the little burners come on, boost the CO2 levels up, and you get improved growth rates out of the plants. And that's one of the things that's kind of cool. You're not only getting heating, but you're getting a CO2 buildup from using an unvented heater. It's kind of a dual purpose thing. And I'm thinking, okay, we're going to try and do that a little bit with the LED. Now, as you can see on this chart here, I'm leveraging the dual function nature of the unvented natural gas heater, and its CO2 output. I'm doing the same thing with the LEDs. I'm using the heat of the LEDs plus the spectral output. And my thinking is I can play some games. If I'm running PWM, that's a lot less efficient as far as optical output, and same with driving the LEDs really hard. Their efficiency drops down. So I'm thinking I can play some games with that, and I can generate more heat or less heat and vary the spectral content around a little bit by having multiple channels on the PWM output. One of the things I want to think about a little bit is the light and dark cycles and the photochemical efficiency of the plants. And there's some earlier papers on this where they talked about the minimum on time is being too short. The plant then thinks it's in a dark cycle. Now, is that true for all plants or just some plants, or is, this some research that can't be replicated? I don't know, but that's one of the things that the pulse width control modulator chip that I'm looking at it can probably do is I can crank the speed up on it and then take the minimum on time into a very short duration. And the reason for doing all this is then I might be able to get more heat out of the LEDs and spectral content for during the nighttime operations. Maybe to the point I wouldn't even need to use a nichrome wire heater in the base plate of the greenhouse. Don't know, but a lot of things to look at. And the chip I'm looking at using is a PCA 9685. It's a 16-channel 12-bit PWM controller, and it's really cool for this application because I can use many of the channels for LED control, set aside one for purposes of controlling the resistive wire heater, that is if I need to use it. But I can have multiple of these 16-channel devices, and they can be slaved together and synchronized by the clock. And as I mentioned previously with the light-dark cycle research, I can bump the clock rates up quite a bit. So there's some really cool things that this PCA 9685 allows for. I want to talk a little bit about transplantation shock. See, one of the goals that I have is I want to be able to have peppers all year round, and that's cool. I'll be growing them inside. But if I want to do tomatoes, obviously if I have a 5-foot tall thing of tomatoes, maybe I can have one of those in the house in the middle of the winter. But if I'm going to have more for like other people and neighbors and such, hey, you don't want to have that many plants in your house. You're going to have humidity problems. So the game plan is to be able to transplant outside. Well, that poses some problems. You go and grow things inside and it's nice and pristine and everything. Go outside and you got wind going on, you got sun going on, you got rain, hail, everything. Well, we're not going to emulate hail, but what we can do by using the I2C bus and some additional peripherals is we can try and make some measurements as to what's going on outside, replicate them inside, and try and reduce the amount of transplantation shock that occurs and therefore improve the yield. At least that's the game plan. So I want to talk about feature creep to the max with this unit and all the peripherals that are available on the I2C bus. We can do some cool things. As I mentioned before, we got the PWM controller, we got LEDs on there, we got resistive heating. Hey, we could add some more channels of those, bank them together, and we can do an XY LED pattern to simulate the sun's positioning. We could throw in a fan control on there, and we could vary the air velocity to simulate outdoor wind conditions. We could also control humidity and soil moisture, and we could even put using the PWM control, vary the height of a burner for CO2 enrichment. So there's all kinds of cool things we can do with the I2C PWM controller chip. Now we can throw an ADC on there too. We can go and monitor the soil moisture inside, we can monitor the outside. Temperature, of course, there's no rocket science with that. We can look at indoor and outdoor temperatures. We could throw a photocell on there, monitor the solar insolation outside and for our light and dark cycle research, and that'd be pretty cool. We can monitor the wind velocity outside. We can also monitor the soil moisture. All kinds of cool things we can do once you stick an ADC on there. Heck, we can even monitor the CO2 concentration in our indoor greenhouse. Got to throw in our real-time clock on there too, because we want to check our seasonal variations of light and dark cycles, and we can sync to even microclimate data if we pull it off the National Weather Service website. And of course, you got to stick a general purpose IO expander on there so that you can have an LCD, and you can also put a bunch of push buttons on there because people got to have something to poke and twist and turn. That's just the way it is. It's going to be cool. We can put a stepper motor on that GPIO chip, and we could use the stepper for purposes of running a shutter. Say if we needed to have dark germination going on, we could have a shutter slide back and forth. The other thing we could do is we could control the Z-axis height of the LEDs. So as the plants grow, we're maintaining a given distance between the LED emitter and the surface of the plant leaves. It'll be really cool. All kinds of nifty stuff we can do with I2C. So we're going to get back to reality a little bit. We got a little crazy there. We had stepper motors and knobs and push buttons and all kinds of stuff. Ultimately, though, we want to just start out with a simple LED grow light that we can expand. So the game plan is increased leverage of the photochemical efficiency curve for the red, green, amber, and blue LEDs under proportional and constant current control so that we can optimize our electrical usage and plant growth. That's the biggie. Then we want to say, hey, we're going to get some additional electrical efficiency by using the residual heat of the LEDs when they're operated in their lower efficiency modes, so that maybe we can save some bucks by not having to have a resistive wire heater. Then we can say, okay, now we're going to get a little bit crazy. We're going to throw that I2C bus and put some expansions, some ADCs, some RTC clocks, and all kinds of cool stuff on there. But that's down the road. Basically, we want to start out simple, which is the LED grow light, and the I2C bus and the peripherals, that's just icing on the cake. So here's the deal. I got the idea. You guys have the demo board. Send me the board. I'll build the unit. Just the LED grow light part to start with, and we'll see if it works. Thank you.